In this video, we're going to explore how we can create a Voronoi diagram in 3D and 2D. Now, a few days ago, I saw this Blender add-on which can fracture objects into these small, beautiful pieces, and I was inspired to create something similar, but in real time. Now, this project will be divided into two parts. In this first part, I'm going to explain the basic concepts, and then we're going to explore a few different algorithms that we could use. And in part 2, we're going to implement the 3D Voronoi meshes in JavaScript. Here's a list of things that we're going to be covering in this video, and now let's get started. Okay, so first let's see what a Voronoi diagram is, and I'm going to draw some things here. So first, let's say we have a single point on the screen. Let's call this a seed point. Now, for a single seed point, the Voronoi diagram is actually empty because what is a Voronoi diagram? Well, for all the points on this plane, we're going to ask, okay, what point are you closest to? And the answer is we're closest to this single point here. So if I color this cell that this point has created, we can see the whole screen is one cell. Now, let's add 2 points here. And now with 2 points, the situation is a bit different. Now, we can draw a line here that divides the world into two different halves. And if I color these now, you can see the cells will have different colors. So for every single seed point, we'll have a single cell. So for 2 points, we get one edge and two cells. Let's see what happens with 3 points. Now with 3 points, the situation is a bit different again. We can draw certain lines here as Voronoi edges, but you'll see that these lines will intersect in 1 point. And this 1 point here is the Voronoi vertex. So this has divided the world into 3 different cells, as you can see right here. So the question here becomes, how do we construct this diagram? And we're gonna get into that in just a second. So let me simplify this and explain what's happening here. So for these 2 points that I marked here, we're gonna have a line that connects these 2 points together. And if we draw that line, you can easily see here that we will get a 90-degree angle here. That is because the Voronoi edge here is the perpendicular bisector of the line that connects these 2 points. And as you can see here, this is again true here. And again, the same thing. So the Voronoi edges are the perpendicular bisectors of the lines that connect these points. Okay, so now if we draw them in a cleaner fashion, the lines will be like this. And as you can see, this gives us a triangle. So that's very interesting. So if we create a triangle set and basically draw the perpendicular bisectors to the triangle edges, we can get the Voronoi diagram. But let's see if this is true for more points. So let's add one more point here. And okay, we have 4 points, and we can triangulate these in a way, and that will help us to reach the Voronoi diagram. Now the problem is, if I draw multiple triangles, you will see that we can either divide the space like this, or we can draw the edge like this. Now we have 2 choices here. Which one is correct? So here we're gonna get into a concept called the Delaunay Triangulation. And that's going to help us reach the Voronoi diagram, but we have to realize what a Delaunay triangulation is. The basic rule of the Delaunay triangulation is that if you draw every circumcircle of the triangles that you have, no seed point should be in the circumcircle of any triangle. So let's see what that means here. So if I draw the circumcircle here of this triangle, you can see it would look like this. Now, this point is in the circumcircle of this triangle. So this is not a Delaunay triangulation, and we've made a mistake. So we need to actually draw the edge like this. And this is the Delaunay triangulation. Now, how can we check that? Well, we can check it again by the same rule. Draw the circumcircle of every triangle in the set, and no vertex or no seed point should be in the circumcircle of a triangle, and this rule applies here. Now, one interesting thing is that for a set of finite points on the plane, we can always draw a Delaunay triangulation, and it is unique. Like, we don't have two Delaunay triangulations for a set of finite points on the plane. So next, let's see how we can use this to create a Voronoi diagram. So let's say that I have a couple of seed points here. Let's go for 5. And we want to draw the Voronoi diagram of this. So let's first create the Delaunay triangulation. And the Delaunay triangulation will look something like this. Now let's draw the Voronoi diagram. So we need to draw the perpendicular bisectors of the Delaunay triangulation edges. So you can see here, if I draw this edge and if I draw this edge, the intersection point will always be outside of the triangle. So let's first draw this edge, and let's draw this edge, and let's draw the final edge here. And let's repeat that for all of the edges. And now we get the Voronoi diagram. Now, this is an okay solution for finding the Voronoi diagram, but it can be tricky to find the vertices here, because you will have to constantly think that, okay, where are the edges are gonna intersect. So the question here is that, is there a better solution or a better way to create the Voronoi diagram from the Delaunay triangulation? And the answer is yes. And I'm going to show you how you can do it. So let's focus on this triangle that I mark here. Now, with this triangle, we have the Voronoi edges and we have the Delaunay edges. Now, if I zoom in on this, let's focus on this edge and this edge. Now, the cool thing about the perpendicular bisector is that if I pick any point on this orange edge, it has the same distance to both this side and this side. Now, how is this useful? I'm going to explain in a bit. We can pick the vertex here, the Voronoi vertex. Now, this Voronoi vertex here has the same distance to this seed point, and it has the same distance to this seed point. And very interestingly, because this is the perpendicular bisector here again, it has the same distance to this point, and it has the same distance to this point. And essentially, the distance here to all of these seed points are the same. Well, how is this useful? Well, if we draw the circumcircle of this triangle here, we can see here that this vertex, this Voronoi vertex here, is the center of this circle. And my drawing is kind of bad here, but you can see that this is R, the radius, and this is R, and this is R. So for creating a Voronoi diagram for a set of points on the plane, we can simply construct the Delaunay triangulation, and then we can calculate the positions of the circumcenters of those triangles, and then we can connect those vertices together to construct the Voronoi diagram. One question still remains: how do we construct the Delaunay triangulation of a set of points in the first place? And here we are going to discuss a few different algorithms. So there are a couple of different types of algorithms which you can use for constructing the Delaunay triangulation. And there are incremental types, there are flip-based types, and you can see all of these algorithms listed in the Wikipedia page. I think the Wikipedia page of the Delaunay triangulation is the best place for you to look through these algorithms. The first algorithm that I want to talk about is the Boyer-Watson algorithm. This algorithm works in 2D and 3D, and it is very easy to implement, but it is not the fastest algorithm in this list. This is the algorithm that we're going to be implementing in the next part, because based on my original goal, I wanted a simple solution and I didn't really care about the speed. So I went for this algorithm. The next algorithm, which only works for 2D, is the Fortune's algorithm. Now, this algorithm is based on the binary search, and it is fairly fast and it is simple to implement. There are multiple articles on this algorithm. I will link all of them in the description if you're interested. Now, the next type of algorithm is the divide and conquer algorithm. Now, this is not an algorithm itself, it's just a category for a few different algorithms that people have invented. Now, the best option here, in my opinion, is the Dwyer algorithm, and I will post a link to the GitHub page of this algorithm in the description. And the next type of algorithms that I want to mention is the flip-based algorithms. Again, this is a category, and I will post some links in the description to some papers on the flip-based algorithms. But okay, maybe you want to use a library for this, you don't want to implement any of this yourself. Well, I have a couple of libraries for you. Okay guys, that's it for this video. In part 2 of this video, I'm going to be explaining the Boyer-Watson algorithm, and we're going to be implementing it in JavaScript with the help of a library called 3JS. So if you're interested in that, go ahead and watch that video next. But before you watch that video, like this one if you enjoyed it, because that simply helps our channel a ton. And with that being said, I'll see you guys next time.